Good evening, viewers. So, welcome to another edition of NAMSSN tutorial. So, this is a partial differential equation. My name is Kamal, by the way. So, today we want to look at the solution of partial differential equation, second order partial differential equation. So, as a matter of fact, we have three analytical methods of solving second order partial differential equation. The first method is the Euler's method of separating variable. Second method is a Laplace transform method, and then we also have integral transform method. So in this lecture series, we are going to be looking at solution by using Euler method. So we'll be looking at solution of each equation, wave equation, Laplace equation, and some other linear first order partial differential equation. So let's revise the idea of ordinary differential equation. If I have y double prime plus y equals to 0, so this is a second order homogeneous differential equation. So the solution of this one, you find the auxiliary equation. You remember the auxiliary is m squared plus 1 equals to 0. M is plus or minus I, right? So if you want to write the complementary solution, you say y equals to, let's say, a cos x plus b sin x. So this is how the solution of this kind of differential equation will be. So the idea of this, we are looking at Euler method of separation of variables. So what is that separation of variables now? When we have a partial differential equation, we already know that a partial differential equation is an equation involving two or more different derivatives: derivative of x, derivative of y, derivative of t. So we are going to use a substitution. The substitution will split that partial differential equation into two first order differential equations. Then we solve them partially and then we join the solution. So the substitution is, we assume that suppose we have this differential equation 3 du dx plus 2 du dy equals to 0. Let's start with you know that u is a function of x and y now. We know that u is a function of xy, right? So the solution we are going to make is that we are going to say let u, the solution now, be a function of x and a function of y, be the product of two independent variable x and y. Let u equals to x. That x is a function of x and that big y is also a function of y. Assuming that I have a differential equation, a partial differential equation like this, du dt plus, let's say, du dy equals to 0 now. This u now, this u, the solution, we are going to say let u equals to t of a function of t, y and a function of y. That's how we are going to, that's the assumption we are going to make. Let u equals to t of t, y of y. So if I have something like this, du dx plus let's say du dt now, or let's say the square u dt squared equals to 0. So this u now, the assumption we are going to make is that we are going to say let u equals to x of x and t of t, or you say t of t, x of x. They are commutative no matter how you arrange it. So this x is a function, is an unknown function of x, and this t is also an unknown function of t. So what we are going to look into is that our dependent variable. So here we're having x and t now. The substitution we are going to make is let u equals to x t. So if I have Laplace equation, like let's say I have the square y dx squared plus the square y dt squared equals to 0 now. This kind of equation now, what is the solution I'm going to make? I'm going to say let y, the solution, y equals to what? X of x and what? T of t. That's how we are going to start. Okay, so we are going to start with that substitution. Let u equals to x of x and y of y. Then we differentiate partially. So what is del u del x? What is du dx? You know, this is an implicit function now. If I'm differentiating u partially with respect to x, I will take y as constant. I will just differentiate this x, right? So this will be y will be constant. Then we differentiate this x with respect to function x dx dx. That's how it's going to be. So du dx equals to y dx dx. And what is du dy? What is du dy? So that means I want to differentiate this function partially with respect to y now. X will be constant. So if I differentiate, I will write x separate, then I will differentiate y. That is dy over dy like this. So it means that these two substitution is what I'm going to make for this problem now. Anywhere I see du dx, I'm going to change it to y the big S the small s. And this du dy, I'm going to change it to x the big Y the small y. So if I now substitute for these guys now into, this is the problem we are solving. Let's say this is 1. So this is 3 du dx now. It will now be 3. This du dx is y the big S the small x plus 2 du dy now. 2 times du dy is x the big Y the small y equals to 0, right? So it's getting messier. So we're having y x now. So what I'm going to do next is to divide both sides by xy. So I'm going to divide both sides by xy. You say divide both sides by x and y. So automatically now the variable will separate. What is separation of variable means that, like we are collecting like that, x should go to x side, y should go to y side. So if I divide both sides by xy, if I divide this side now by xy, and I also divide this side by xy upon xy, this y will cancel. So we are going to have 3 over x the big S the small x, right? If I divide this side by xy, x will cancel. We are going to have plus 2 over y the big Y the small y equals to 0. Can you see that the variable has now started separating now? We are having function of x in one side, function of y in the other side. Then move this one to the other side, because we are calling it partial differential equation. We have so many differential equations, then we are solving them one by one partially. So if I move this one to this side, we are going to have 3 over x the big S the small x equals to minus 2 over y the big Y the small y, right? So in that case, now how do we now solve this separately and solve this separately? So we are going to introduce an arbitrary constant now. We are going to say that this particular function is equals to something, and this one too is equals to that thing. So we are going to say that let's equate them. Let's say they are equivalent to, just bring any arbitrary constant. I will say equals to k now. That means this 3 over x dx dx is equals to k. This minus 2 over y dy dy is equals to k. So when you look at it now, you observe that this is a first order differential equation. This is also a first order differential equation. We're having x and small x, y and small y. So in that case, we are going to have 3 over big S, the big S, the small x equals to k, right? Let me rule a line here. And we're having minus 2 over y, the big Y, the small y, that one also equals to k. What method are we using now? Separating variable. Go back to maths method 1, differential equation. So how do I separate variable here now? Cross multiply. If I cross multiply, I'm going to have 3 over x dx equals to k the small x, right? And if you do the same here now, minus 2 over y dy equals to k dy, right? When you separate variable, the next thing is to do what? Integrate both sides. So if I integrate 3 over x with respect to big S, and I also integrate k with respect to small x, and this side I will also integrate minus 2 over y with respect to big Y, and I also integrate k with respect to small y. If I integrate something over x, that's log now. So this will give us 3 ln x, right? K is a constant. Integrate k with respect to small x, that's kx. Then you say plus c, let's say plus c1, because we are solving two first order differential equations simultaneously. So divide both sides by 3. You know how this one will be. Make this big S as subject. Log x. Where are we going? Where I'm going is that I want to solve for this x, and I also solve for this y, which satisfy my solution. So if I divide both sides by 3, now I'm going to have ln x equals to kx over 3 plus. Now c1 that I introduced here now, c1 is a constant. Whenever you integrate a function, you put plus c, a constant. And 3 too. 3 is a constant. If I say c1 over 3 now, both of them are constant. We can say this one is just k. Let's say we introduce a constant, let's say 5 for example, whatever. So make x as subject, take exponential of both sides. So x here will be e raised to power kx over 3 plus 5, right? And whenever you have e raised to power a plus b, it's like saying e raised to power a, e raised to power b, right? So e raised to power kx over 3 and e raised to power 5. This 5 is a constant, don't forget, and e raised to power 5 is also a constant. So we are going to say this is x equals to, let's say e raised to power 5 is a, it will be a exponential kx over 3. That is the solution of the first one. Now do the same here now. Integrate minus 2 over y, that's minus 2 log y. Integrate k with respect to y, that's ky, let's say plus c2. Divide both sides by minus 2. Log y equals to minus ky over 2. c2 is a constant. When you divide c2 by minus 2, that one too is also a constant. Let's say plus psi. Anything, you can say plus k, plus m, plus anything, just know that this is a constant. Make y as subject, y equals to e raised to power minus ky over 2. You know, we are going to have e raised to power psi here as well. Let's say that one is b. Let's say that one is b. So this is the solution for y partially. This is the solution for x partially. X is equals to a exponential ks over 3. Y equals to b exponential minus ky over 2. So what is our assumption? Our assumption is that our solution is what? X of x, y of y. So if I now put it back now, don't forget that my solution u of xy, the solution is equals to x of x, y of y. What is our x of x? Our x of x is a exponential kx over 3. That is a exponential kx over 3 dot. What is our y of y? B exponential minus ky all over 2. A times b, 2 constant. A times b is also a constant. AB is a constant. So we can say that our solution u of xy equals to, let's say, c now. If I say that AB now, if I call it C, because both of them are constant. In partial differential equation, the product of constants is a constant. So anyhow you can operate it. So A times B now, you can leave it as AB, there is no problem. Just know that they are both constants. AB is C, right? You know here now, e raised to power kx over 3, e raised to power minus ky over 2. You can say this is e raised to power k x over 3 minus y over 2. I hope you know this is indices. Join them together. So that is our what? Final solution of this 2 something equals to 0. So using Euler method of separation of variables. So that is one example. So if you did not understand anyone, you can just go back, pause the video, try again. So we are basically applying what we learned in mathematical method 1. So let's solve du dx equals to 2 du dt plus u. So this one is a boundary condition. It has u of x comma 0 equals to 6 exponential minus 3x. You know, when you are solving boundary value problem, after you are done solving, say that when x is equal to something, y equals to something, to get that k. So that is this kind of problem. Now, u is a function of x and t. According to what I said at the beginning, what are we going to make as our assumption? Solution, we are going to say let u equals to what? T of t, x of x, right? You can say x of x, t of t. Then you differentiate partially. We need du dx. What is du dx? Du dx is we are going to take t as constant, differentiate x partially. It will be t, the biggest, the smallest, right? And also, what is du dt now? X will be constant. Differentiate t with respect to small t. So we are going to substitute these two guys into the problem we are solving. We are solving du dx. What is du dx? Du dx is t, the biggest, the smallest, right? So if we substitute now, we are going to have t, the biggest, the small x, is equals to 2 du dt. Du dt is x, the big T, the small t, plus u. What is u? U is what? Tx, or you say xt. So u is equals to, let's say, tx. All right. This one is just telling us that this t is a function of t. This x is also a function of x. You can just say tx. All right. What are we going to do now? What I said earlier, you divide by what this time around? In the previous example, we divide by xy. This time around, we divide by tx. So when you divide by tx, what are we going to have? So automatically it will separate, the variable will separate. So if you divide by tx, now if I divide this one by tx, divide this one by tx, divide this one by tx, t upon t, we are going to have 1 over x, the biggest, the small x, right? is equals to divide by tx, s cancel s. We're going to have 2 over t, the big T, the small t. You divide this one by tx, that's plus 1, right? Now, x and x have been separated, t and t has been separated, and 1 is there. So we are going to assume that we equate them to an arbitrary constant. Let's say it's equals to k, as I said. It means that this guy is equals to k, and this one too is also equals to k. Then we solve partially. So we are going to say 1 over x, the big S, the small x equals to k, right? And similarly, we are going to have 2 over t, the big T, the small t plus 1 equals to k. You see that Euler method will turn that partial differential equation into 2, either second order or first order, depend. So here now you solve this separation of variable, cross multiplying 1 over x dx equals to k, the small x, right? Integrate both sides. Integral of the big S over x is equals to k integral of the small x. If you integrate the s over s, that's natural log of s. If you integrate dx, that's x. So this will be kx, let's say plus c1. Make this s a subject. So x equals to e raised power kx plus c1, right? So that e raised power kx is there, e raised power c1 is a constant. You can change this e raised power c1 to like a. So this is the solution of this x of x. Now let's now move to this one. Now how do we solve this? If you bring 1 to this side, first order differential equation, bring 1 to this side, we are going to have 2 over t, the big T, the small t equals to k minus 1, right? Cross multiply, make the t come to this side. 2 over t, the t equals to k minus 1, the small t, right? Then you integrate both sides. Integral of 2 over t dt equals to integral of k minus 1, the small t. If you integrate 2 over t, that's 2 natural log of t. Now, if you integrate k minus 1 are constants. You integrate all of them with respect to t, it will just be t into k minus 1. Then you say plus c2, right? Divide both sides by 2. Natural log of t equals to t over 2 into k minus 1. Now, c is a constant. If you divide this guy by 2 now, c2 over 2 is also a constant. Let's say plus another constant. Let me even call it c2 again. It doesn't matter. Okay. So take exponential of both sides. T equals to exponential, everybody here, t over 2 into k minus 1. No, we are going to say plus c2. And you know that e raised power constant is also a constant. So let's say this e raised power constant, let's call it down b. Do you get? So this is the second solution now of this guy. So now go back to our assumption. What is our assumption? We assume that u equals to what? We assume that u equals to t of t, x of x, right? So what is t of t? This is t of t. What is x of x? This is x of x. Pack them together. So it will be a exponential kx times b exponential t over 2 into k minus 1, right? A times b is a constant. Can join them. You can say that let your a be, let's call it c, doesn't matter. So u equals to c e raised to power now. So this is e raised power kx, this is e raised power something. You can say this is e raised power kx plus, you remember now, this is kx plus t over 2 into k minus 1, right? So this is our general solution. But then it comes with another condition. What is the condition? U of x comma 0 equals to 6 exponential minus 3x. What does that mean? So that condition will let us find the value of this c. Now, let me write it again. U equals to c exponential kx plus t over 2 into k minus 1, right? So we have u of x comma 0 equals to 6 exponential minus 3x. It means that, you know, our problem is u of x and t. It means that this t, we started with u of xt, right? Because the problem is the u dx and the u dt. It means that this 0 stands for t. It means that when t is 0, our u is this 6 exponential minus 3x. Do you understand? When t is 0. So now, in this problem now, put t as 0. Now, if t is 0 here now, everybody here will turn to 0, right? If t is 0, everybody here will turn to 0. And u is 6 exponential minus 3x. It means that 6 exponential minus 3x equals to c e raised power kx. Because if t is 0, every part here will go. Oh yeah, now equate. When you equate, c is 6. right? Yes, now. So c is 6, and then this and these are equal. Minus 3x equals to ks. K is minus 3. All the constants now, we'll find them. So when we know k and c, now return them back to your general solution. So our general solution is, do you understand what I'm doing? If t is 0, if t is 0, it means that when we have 0 over 2 times anything here, it will turn to 0. So it will only remain this part. Okay, so we are having it here, and that u is 6 exponential minus 3x according to the condition. So put the two values back into your general solution. Our general solution is u equals to c. C is 6 exponential ks. We've gotten our k now. K is what? Minus 3x plus t over 2 into k is minus 3 minus 3 minus 1 minus 4. When we put minus 4 here now, 2 and minus 4, that is minus 2t. You see, that's how it will be. And so this is how the solution will be, right? So let's go into the application of what we have been learning. So let's solve each equation, let's solve wave equation, let's solve Laplace equation. All right, so let's now apply those 3 examples to solve the problem now. Wave equation, heat, and Laplace equation. So wave equation arises from the equation of vibrating string from what do we call it, mechanical wave. So now this is how wave equation looks like. Suppose we are asked to solve, let's start with wave equation now. Wave equation. Suppose we are asked to solve this problem, d square y dt squared equals to c squared d square y dx squared. So with this condition, y of 0 comma t equals to 0, y of l comma t equals to 0, y of x comma 0 equals to f of x, and d dt of y of x comma 0 equals to 0, and s starts from 0 less than x less than l. So this is the problem we want to solve now. D square y dt square equals to c square. This c represents the speed of the wave. You know, when you are having a wave now, wave exhibits some properties, amplitude, frequency, speed, and all that. So this c represents the speed of the wave, okay? So it's a constant. So how do we start now? We start by saying let u equals to what? Oh, we are not using u. This is y. Y is the y is what we are solving for. So we say let y equals to what? T and x. So x of x, t of t, right? So in that case, what is dy dt? Dy dt is equals to what? We are differentiating with respect to t, keeping s as constant. It will be x dt, the small t, right? What do we need? We need the square y dt square, okay? So what is let me put it here. The square y dt square. Then we are still differentiating this thing again with respect to t. X will t be constant. Then we differentiate t, that's the square t, the small t square, okay? That's how it will be, the square t, the small t square. Now we also need, what is dy over dx? Dy dx, it means that we are keeping t, differentiating x. This will be t, the biggest, the small x, right? And then we need the square y, the x square. We are keeping t again. We are differentiating this guy to be the square s, the small x square, right? So that's how it will be. So what are we substituting for? We are substituting for the square y, the t square, and the square y, the x square. Okay. So put them into the problem we are solving. So we are substituting this guy alone. If we substitute, then we are going to have the square y dt square is equals to x the square t, the small t square, c square. The square y dx square is what? T, right? The square s, the small x square. Okay. So after that, we equate them to something, right? So oftentimes I usually equate it to k, equate it to c. So because I'm solving second order now, you can say it's equals to k, you can say equals to minus k. So I will say equals to minus k squared. If you use k, you still get the same thing. But the difference is that if I use k now, suppose I use just k. Now I'm going to tell you the difference if you use k or when you use k squared. You know, in complex analysis, you did a circular function, sin x. You know, sin x can be expressed as exponential ix minus exponential minus ix over 2i. If you use just k as your arbitrary constant, your answer will be in exponential form. And that exponential form can be changed back to trig form. But if you use minus k squared, your answer will be in form of sin x plus cos x, which is also exponential of e and e minus I. Okay, don't worry, when we get there, I'm going to talk about it very well. So now if I separate it to the minus k square, it means that x the square, oh, before I separate, sorry, I will divide by xt this time around. So I'll divide by xt. If you divide by xt, it will automatically separate. Now if I divide this one by xt, divide this one by xt, x cancel, we are going to have 1 over t the square t the small t squared. If I divide by xt, t cancel, it will be c squared over x the square s the small x squared. Now I'm going to separate it with minus k squared. Minus k squared. Okay. So this is equals to minus k squared, this is equals to minus k squared. So we are going to have 1 over t the square t the small t square equals to minus k square, and also c squared over x right, the square x the x square equals to minus k square, right? Now what do we have now? We have two second order differential equation. The previous example we usually have two first order. Cross multiply now, cross multiply the square t now is equals to, if you bring everything here, is equals to minus k square t the t square, right? Now bring all of them back, right? Oh, no, you don't need to cross multiply, just multiply by t, this is second order. You multiply by t, we are going to have the square t the small t square equals to minus k square t, right? And also if you multiply by c square s, so if you divide by c square s, we are going to have the square s the x square equals to minus k square x k square cx, like this. That's how we're going to have. Now bring this one to this side. Bring this one to this side, we are going to have let me solve here, solve here. Bring this one, we are going to have the square t the small t square plus k square t equals to 0, like this. You know, at the beginning of this video, I talk about how to solve for second order. I make y prime plus y. So this is an illustration now. The square t the t square plus k square t equals to 0. This is what? This is a second order differential equation. How do we solve this? Find the auxiliary equation. What is the auxiliary equation here? Auxiliary equation will be m square plus k square is the constant. K square equals to 0. If we bring this one to this side, it will be m square equals to minus k square. The solution will be no, we are going to take the square root. So m equals to plus or minus ik, right? Because when you take the square root of minus, it's complex number. So if m equals to plus or minus ik, if you remember in maths method 2, when you have complex solution, if the root of auxiliary equation is complex, how will the general solution be? It will be in form of sine and cos, right? So it means that I will just say my t of t now, the solution it will be, let's say c1 cos, now our k cos kt. You know, we are solving for t. C1 cos kt. Oh, sorry, viewer, sorry. So let me put it here. When you have this now, the solution will be t, right? T of t equals to c1 cos k. K is here. Cos kt plus c2 sine kt, right? This is the first solution of this PDE. Then you solve this as well. And if you solve the second one, if we are solving the square x, the x square equals to minus k square c square. Don't forget, c is the speed of the wave, all right? Now bring all of them to this side. We are going to have the square s the x square plus k square c square x equals to 0, right? Now what is the auxiliary equation of this one? The auxiliary equation will be m squared, right, plus everybody here are the coefficient of this x. So m squared plus k square c squared equals to 0. Bring them here, then solve. M squared equals to minus k square c squared. Take the square root, right? So m will now be plus or minus, right? IKC, because when you take the square root of k square c square, it will be kc. But then because of this minus, it will have I. So what is now the solution of this now? What is the solution of this guy? So it will be x of x now. X of x equals to what? If I'm using C1, C2, my next arbitrary constant to be, I can say C3, C4. So I'll say C3, this one too will take cos k cx. We're solving for x this time around, plus c4 sine kcx. All right, so this is how the second solution will be. This is the first solution, this is the second solution. So where are we starting from? We are starting from y equals to x of xt of t, x of st of t. Now join them together. So if you join them together, what will now be your general solution? The general solution, I'll clean this side now. So the general solution will be y, so it's a lot. So y equals to x of st of t. So this is my x of xt of t. C1 cos kt plus C2 sine kt. That is the first one. The second one is C3 cos kcx, C4 sine kcx. All right. So if you have that, C1, C2, C3, C4, they are the arbitrary constant. In fact, K2 is included. K2 is a constant. So let's now, I've cleaned all the condition. So you now start using the condition one by one. So what is the first condition? This is the general solution without the boundaries. So the first boundary is what? The first boundary condition is y of 0 comma t is 0. What does that mean? No, we are solving for y of t comma x. So here we are solving, this is y of 0 comma t. It means that this condition means that when x is 0, the solution is 0. When x is 0, the solution is 0. So from here now, where is x is 0? Anywhere here. If x is 0 here, if x is 0 here, if the solution is 0, if x is 0 cos 0 here, it will be 1. No, cos 0 is 1. If x is 0 here, sine 0 is 0. So it means that this part will no longer exist. So we are going to have 0 is equals to c1 cos kt plus c2 sine kt. Everybody here turn to 0. So it will just remain c3. All right. So don't forget what I said earlier on, that when we have two things, the product of two things equals to 0. So obviously this larger one will no longer give us 0. It is this c3 that will be 0 here. When we have everything here times this c3 is 0, it means that c3 is the 0 part. All this one will not turn to 0. So if c3 is 0 now, the solution will now started what? It started reducing gradually. So c3 is 0. It means that our new solution will not include this part again. So y is equals to, we are going to have c1 cos kt plus c2 sine kt, right? So we are not having c3 part anymore. Then c4 sine kcx. That's the new solution. So that is condition 1. The second condition now, what is second condition? The second condition is y of l comma t is also 0. What does that mean? No, we are solving for y of x and t. It means when x is l, the solution is 0 at l. So when x is l, y is 0. So if that is the case, y is 0 now. Anywhere you see x, put l here. Anywhere you see x, oh, x is not here, x is here. So we are going to have, well, c1 cos kt, this side will remain, c2 sine kt, c4 sine what? kcl. All right. Now, everything here multiplying this one is 0. Now, what are we going to equate to 0? It is this part that will give us the 0. But then, I need to be very careful. We have L here. We have sine function here, and we also have C4 here. If I say, oh, because this one can no longer be 0, C4 is 0. No, if I say C4 is 0, it means that there won't be anything here again. Because I've already said C3 is 0 in first place. If I say again that C4 will be the 0, it means that this solution is trivial. No solution. So I will not say C4 is 0. I would rather say this sine KL part is 0. So I'm going to say that sine KCL will give us 0. That one will give us something. So how do we solve this? What is a sine? We know that sine is an odd function. Sine 0 is 0, sine 180, sine all that is 0, right? So I will say this is sine KCL is equals to sine n pi, because for all n from 1 to 3, sine n pi are 0. Okay. So sine cancel sine. It means that KCL equals to n pi. Don't forget, c is the speed of the wave, is known. K is a problem now. If you divide both sides by Cl, so K is equals to n pi over what? Over Cl. Don't forget, we divide that K from where we separate the two partial differential equations. So K is equals to n pi over Cl. That's what we are going to say. If K is n pi over Cl, so the new solution you are going to have now. Oh, where did I stop? I stopped at yeah, this is my new solution before. After getting K as n pi over Cl now, anywhere you see K, put it back. See that it will now look messy. We are going to have y equals to what? C1 cos. Now K is equals to n pi over Cl. Okay, so cos n pi over Cl plus C2 sine this K now, n pi. Oh, is having T here. N pi over CLT. Everybody here, then times what? C4 sine K is what? N pi over Cl. And this is KC, right? I multiply this one by C, it will be n pi over Lx. Yeah, that is it. Okay, that's how it will be. This is our new solution. That means we've exhausted two conditions. Now it remains two. So what is the third condition? The third condition is y of x comma 0 equals to f of x. And the last condition is d dt of y of x comma 0 equals to 0. Now, this time around, now I will now use this fourth condition instead of the third one, because I did not know what f of x. F of x is also an unknown variable, unknown function. So I will start with this fourth condition in this case. So what is the meaning of d dt of y at x comma 0? It means that this is our new solution now. When we differentiate it partially with respect to t, when you differentiate this solution now partially with respect to t, and anywhere you see t, you put 0, it is 0. Now, how are we going to do it? So what is dy dt first? What is dy dt? It means that we are differentiating this several variable with respect to t. It means that you only differentiate where you have t. This part is having t. If I differentiate cos, the derivative of cos is minus sine. So this one will give us what? If I differentiate what is here with respect to t, I'm going to have, let me open a big bracket. Everything here, if you differentiate cos 2x, what is the answer? It will give us minus 2 sine 2x, right? So if I differentiate cos everybody here with t, so this one will give us minus n pi over Cl times C1 sine, this time around, sine n pi over CLT, right? Differentiate what is here now with respect to t as well. So this one will also turn to this side, it will be plus n pi over Cl C2. Now sine is cos, right? Cos n pi over CLT, right? Yes. Oh my god. So with this C4, oh, this one is not having t, so we leave that one. C4 sine n pi over Lx. Alright. So now what is the condition? This is our dy dt, right? Now dy dt at t is 0. So our derivative now, when t is 0, that derivative is also 0. That's what it means. That is the meaning of this condition. So when time is 0, now anywhere you see time, put 0. If time is 0, sine 0 is 0. Everybody here will turn to 0, right? If time is 0, cos 0 is 1. So this one will survive. Nothing will happen to this one. So if time is 0 now, we are going to have n pi over Cl times C2 only, right? Multiplying C4 sine n pi over Lx. Dy dt is also 0. Okay? So dy dt is 0. Now, we're having C2 and C4. What are we going to equate to 0? You know, n pi over Cl are constant. We know n now. N starts from 1, 2, 3. C is the speed of the wave. L is the length of the spring, because this is wave equation. So all these are constants. All these are constant. Now, it now remains C2 and C4. Now, what are we going to equate to 0 between C2 and C4? If I say C4 is 0, don't forget, if I say C4 is 0, I'm going to have 0 solution. And that's not possible. So what I'm going to take to 0 is C2. So I'll say C2 is 0. If C2 is 0 now, this is our solution now. What is our new solution now? Our new solution is y equals to, now C2 is 0. Everybody here has vanished. So it will now remain C1 cos n pi over CLT. Everybody is 0 here. Then C4 sine n pi over Lx. Alright? So it remains one condition now. But we have one condition, but we still have two constants. So what we are going to do is that we are going to collapse these two constants, C1 and C4, to be a single constant, because constant multiplying constant is also constant. So C1 times C4, you can say that one is just Cn. I say it's just C. So I'm going to say this time around, why am I doing that? It's because I only have one condition left. Every condition you have in partial differential equation will solve constant. If you have one condition, you solve one constant. Two conditions, you solve two. So we have four conditions, and we have like, well, I think we have three conditions, and we have like four constants. So it's not enough. So we are going to say let C1, C2. Let's call it C this time around. Let's call it C. So we have the solution will now be y equals to C1 times C2 is C, right? So y equals to C cos n pi over L T sin n pi over Lx. So join them together. So it will now be cos n pi over CL T sin n pi over Lx. Don't forget, your solution must have, let's say C2. Okay, let's say Cn, so that it will differentiate this one from constant. Your solution must have x. Oh, thank you, Cn. Thank you. Oh, let's C1 and C4. Thank you. Yes. You see that we are getting it. Our solution is still having T and X. Yeah, we are getting it. Now, let's now use this last condition. What is the meaning of this condition? Y of x comma 0 equals to f of x. It means that when t is 0 now, y of x comma 0 equals to f of x. It means when t is 0, that y is a function x where we don't know. How do we apply that condition? This is how we apply it. Now, anywhere you see t, put 0. Anywhere you see t, put 0. If I put 0 here, we are going to have cos 0. Cos 0 is 1. We are having y equals to Cn now. Okay? Then, okay, let me write it first. This one is 0. It will be Cn sin n pi over Lx, right? That y is what? We call it f of x this time around. F of x equals to Cn sin n pi over Lx. Now go back to this thing. What does it look like? 1 second, just think, what does it look like? Go back to Fourier series. Do you remember Fourier sine series? Fourier sine series is equal to integral from something, f of x sin x, f of x cos x. So what we are having here now, in order to find this Cn now, we are going to take the Fourier sine series of this f of x. Well, f of x is not defined. So I will say that it is Fourier sine series. So how do we take Cn now? So Cn is the Fourier sine series of f of x, because we are having sine left. If it is cos now, it is the Fourier cos series. So Cn is equals to, what is formula of Fourier sine series? 1 over 2 pi. If it is from domain of pi to minus pi to pi, I'm going to say 1 over 2 pi integral from a boundary f of x sine pi x over L or something. So Cn will now be integral of f of x sine n pi over Lx dx. From where? Is 0 to L. So, and what is Fourier sine series? 2 over L. If you remember, it's 2 over L something. If it is normal Fourier, it will be 1 over 2 pi. So Cn, so this problem, it encompasses so many things that you need to go back and do revision about. So Cn is equals to 2 over L integral of f of x and n pi s over L. So now, what is our, return this Cn guy to your solution now. Finally. So y equals to, what is Cn? Cn is equals to 2 over L integral from 0 to L. That f of s, leave f of s as f of s. F of s. I'm putting Cn back into my final problem. f of s sine n pi over lx dx times what? Cos n pi times, no, this is dx, so we are integrating this with respect to x, so it does not concern this one. This is function of t, cos n pi over cn t. Finally, that's it. This is how our solution will be. Assuming that f of s is defined, and let's say they give us f of s to be like x square, x cube, then we now take Fourier series again. You know, for you to take Fourier series, you're going to do integration by parts. So the problem is just limiting at f of s is f of s. So again, make u equals to xy, differentiate, put condition. So that is one solution of wave equation where f of s is not defined. So it has the same algorithm for all wave equation. All right, so this is another example. Let's solve this d square u dx dt equals to exponential minus t cos s. So let's try other one. So u is a function of what? X and t. According to Euler method, we are going to say let u equals to x of x, t of t, right? So what do we need? What is du dt? You know, from partial differentiation in calculus, when you have something like this, d square y, let's say dx and dz, it's same thing as having it as d square y dz dx. Both of them are commutative, so no matter how you arrange it, they are equal. So what is du dt? I will start with du dt, then I will do the square u. So du dt is x, right? X will be constant. This one will be dt, the small t, right? And then we then need the square u over, that means the square u dx dt. Now to get this, it means that we are differentiating with respect to x our du dt, right? We are differentiating with respect to x our du dt. We are differentiating this guy. So it will now be, if I differentiate this thing again, if I differentiate x, it means I'm differentiating with respect to x dt, the small t, right? Now when we have two functions, what are we using? Product rule, you remember? So how do I differentiate this thing that I've already gotten again with respect to variable x? Now product rule, you differentiate one, you keep the other one. If I first differentiate x, that will be the big x, the small x. You know, I'm going to leave this, the t, the small t, right? Plus, that is like v du, then plus u dv. Now you will now keep this x, you will differentiate dt dt with respect to s. Now what is the meaning of dt dt? A function of t. Now you want to differentiate a function of t with respect to s, that's 0. Like if I have t squared, if I want to differentiate t squared with respect to x, no, t squared is not x now, it will be 0. So if I want to differentiate this dt dt with respect to x, that's 0. So it means that this side will no longer be there. It means the square u dx dt is equals to dx dx dt dt. So this is the solution we are going to make back to our problem. So the problem is d square u dx dt now. So it means we are having this d square u dx dt is the big S, the small x, the big T, the small t, is equals to what? Is equals to exponential minus t cos x, right? Now what do we do now? We separate. This time around we are not dividing by tx, we did not have tx. So if I divide both side by dt, the small t, so that it will move to this side. If I divide by the big T, the small t, what are we going to have? Already this side now, it will remain just the s dx here. Now if I divide this side, we are going to have exponential minus t cos x over the big T, the small t, isn't it? Okay, so when we have something like this big T will jump up. So we are going to have exponential minus t cos x. We are going to have the small t, the big T, like this. Okay, that's what we are going to have. So the big S, the small x, is equals to the small t, the big T, exponential minus t cos x, right? Now if I now divide both sides by cos x, if I divide both sides by cos x, we are going to have a divide, just to separate, divide by cos x, we are going to have the x over the small x divided by cos s over cos s, right, is equals to the small t, the big T with e minus t here. So the variable has been separated. Okay. So after we've done separating the variable, then we equate it to any arbitrary constant. Suppose we equate it to like k, as I've been using dx equals to k. So it means that this side is equals to k, this side is also equals to k, isn't it? So we then have, let me separate now. We are going to have the big S, the small x over cos x equals to k. I don't want to jump to sec. Okay, is equals to the small t, the big T. Oh, I'm missing those t up. The small t, the big T exponential minus t equals to k, right? So we'll separate them now. Cross multiply. If you cross multiply, what are we going to have here? We are going to have the big X, the small x equals to k times cos x, right? Then you separate again, you cross multiply again, so that all those small x will come to this side. So if you cross multiply again, we are going to have the big S equals to k cos x, the small x. All right. So this side too now, if I cross multiply the small t with e minus t equals to k the big T, right? Yes, we'll separate them. Small t are already here, big T are here. So after separating, what's the next thing? Integrate both sides. If I integrate this side, we are going to have integral of the big S equals to integral of k cos s the small s, right? Is also same thing as doing integration here. So integral of exponential, integral of what? What are we having here? Oh, this is dots. Integral of exponential minus t the big T equals to integral of k the capital T, right? If I integrate the biggest, I'm going to have x. If I integrate cos, integral of cos with respect to x is sine, right? So this one will be k sine x, let's say plus c1. This one does not have link that we are going to say exponential on both sides. So if I integrate exponential minus t with respect to t, it will give me minus exponential minus t, right? If I integrate k with respect to t, it will give me kt, let's say plus c2, right? Now, our aim is to make t and x to stand alone, right? If you return this c here now, so we are going to have kt. Okay, let me just make it a subject. So t is equals to minus c minus exponential minus t, right, over k. That's it now. Don't forget that c is a constant. So this c2 that I put here is a constant, and k, where exactly, where is it coming from? Yeah, this arbitrary constant now. So this c2 over k is a constant. So we can say that t is equal to, we can even say everything here now is c2. Does not matter. c2 minus exponential minus c, so that it will make sense, right? So this is our t of t. This is our x of x now. What was our assumption? Our assumption is, we said that let u equals to t of t, x of x, right? So u equals to, what is t of t? This, x of x, this is equals to k sine x plus c1 into bracket c2 minus exponential minus t. So this is our general solution. So the next thing is to, sorry, I've cleaned the condition. So this is the general solution now. But then this problem comes with some certain conditions. Okay. So what are the conditions? The condition is that given that u equals to 0 when t is 0, that one will solve one of, we have two constants now, c1 and c2. So when u is 0, t is 0, let's use that one first. If u is 0, this one will be 0. Anywhere you see t, put 0. Maybe put 0 here, this guy will be 0. Or if I put 0 here, e raised by 0, it will be 1. Sorry. So I'm going to have k sine x plus c1 into c2 minus 1, right? Into c2 minus 1. That's how it's going to be, because everything here is 0. Now, look here carefully now. Whenever you are solving partial differential equation and you arrive at this kind of problem, what are we going to equate to 0? Is it this one to 0 or this one to 0? Now, look at something. If I have 2 times something is 0. If I say 2 times something is 0, obviously, what is there is that 0. Because 2 is clearly not 0 now. It means that this box, it will be the 0. 2 is not 0. So if I have everything here now times something like this, it will give me 0. Obviously, sine function, we have sine 1, sine 2, sine 3, sine 0.4. Everything here can never be 0. Everything here can never be 0. It means that this part is the one that will most likely turn to 0. So we are going to say that c2 minus 1 is 0. We are not going to equate this one to 0. That's how partial differential equation have been solved. You can't say both of them are 0. So if C2 minus 1 is 0, it means that C2 is equals to 1. All right. So if C2 is 1 now, return C2 back to your general solution. So it means that U equals to K sine X plus C1. C2 is 1. So this will be 1 minus exponential minus T. All right. But then there is another thing. C1 and K, we have not gotten them. They are both constant as well. So the second condition is that the du dt is 0 when x is 0. That is the second condition. We call this one when du dt is 0. Now, what is du dt? When I differentiate this my new solution partially with respect to t. Now, if I want to differentiate something partial derivative, I will only differentiate that t part. I will leave the others, right? So what is du dt now? What is du dt? It means that I will just differentiate this part. If I differentiate this guy now, it will turn to, let me just put it here, it will turn to 1 plus, right, e minus c, because this minus will come here, times k sine x plus c1. You know, we are not touching this part because we are differentiating with respect to t. Now when this du dt now, when it's 0, x is also 0, it means that in my derivative, in the derivative that I just made now, I will put 0. That is 0 equals to x is 0. If x is 0, no, we are going to have k sine 0 here, and sine 0 is 0, right? So we are going to have 1 plus exponential minus t into bracket. If I put x at 0 now, everything here will turn to 0, c1, right? That's what we are going to have now. Now, we have this guy multiply this guy, giving us 0. Now, which one obviously will not turn to 0? This part will not turn to 0 because exponential function starts from 1. Exponential x 1 plus x squared like that. So everything here will not turn to 0. It means that it is this c1 that will be 0. So it means that c1 is 0. After getting c1 at 0, go back to our new solution. What's our solution? This is our solution, right? This is our solution. Our solution is u equals to k sine x. C1 is already 0, fine, times 1 minus exponential minus t, right? So you can open the bracket. U equals to well, 1 minus exponential minus t times k sine x. That's how it will be. All right. So C1 and C2. Yeah, there is no more condition again. So this is our final solution for this problem. All right. So if you are not clear with any of my evaluation, just pause the video, go back, watch it again, go back, watch it again. So that's it. So let's now move to application. Let's solve each equation, wave equation that will mostly come out in our exam using this Euler method.
So this is another application. This is each equation, one-dimensional each equation. Now, where is it coming from? Now, this is an AC. Let's assume that the temperature, the output temperature is like 12 degrees Celsius now. So this side that I'm in now is cooler. And let's say this side, that side, the AC is not reaching that side. So let's say that side is, the temperature of that side is like 22. So how does this coolness, how does it move from here to here at every time? So at each component at this point now, so the temperature can be like 13. When I move to that point, it can be like 17. So what is the temperature of this room now? So that is where this heat equation arises from. So we want to find the temperature, we want to find U at every domain. So that is where this guy is coming from. So we are solving for U. T and X are the variables. So we say let U equals to xt as usual. So I'll jump a step now. We need the square U dx square, right? So what is the U dx? That's T dx dx. What is anyway, let's do it. What is the U dx? The U dx is T, the d dx, the small x, right? So the square U dx square is T, the square x, the small x square, alright? So we need this here now. Now what is du dt? Du dt, if u is equals to xt, what is du dt? Du dt is x, is big T, the small t, right? So we also need this guy. So put it back into the problem we are solving. So we are having du dt is x the big T the small t is equals to the square u the x square now is equals to t the square s the small x square. Then what are we going to do? We divide both sides by x and t so that the variable will separate. We divide by xt, xt, xt. So this will be 1 over t the big T the small t is equals to 1 over x the big S the small x square. So we are going to say this thing is equal to an arbitrary constant. So I'm saying minus p squared this time around. It doesn't matter, I can say minus p. So if I say it's equals to minus p squared, we are going to have two differential equations, one first order, the other one second order. So 1 over t the big T the small t equals to minus p squared, and 1 over x the square s the small x squared equals to minus p squared. Alright? So this is first order now. First order, first derivative. Variable separate. The big T over big T equals to minus p squared the small t. Integrate both sides. The integral of the big T over T is equals to minus p squared integral of the small t. This will give us log t, right? To just integrate the t, that's t minus p squared t, right? Plus c1. So t equals to e raised power minus p squared t. And e raised power c1, let's call it c1. It doesn't matter, let's say it's c1. Okay? So how do we move here now? Multiply by x. The square s the small x square equals to minus p square big S. Bring this one. The square s the small x square plus p square s equals to 0. Because this one is a second order differential equation. So that is variable separate. So what is the auxiliary equation now? M squared plus p squared, because p squared is the coefficient of x, equals to 0. Bring this one, it will be m squared equals to minus p squared. Take the square root of both sides. So what is square root? I, right? Plus or minus p. So what is the solution now? X of x. Oh, I'm using C1. I will say this one is C2 cos px. Alright, so small x is the dependent variable plus C3 sin px. So these two guys now, join them together. Where are we joining it? U equals to xt. So but u equals to xt, so that means our u equals to x and t, c1 exponential minus p squared t into bracket c2 cos px plus c3 sin px. Alright? So this is our general solution without these jargons. Oh, we have 1, 2, 3 condition. 1, 2, 3 constant. So I think this one will work. Well, let's see. Now let's now start putting the condition. What is the first condition? U of 0, t equals to 0. U of 0, t equals 0. It means that when x is 0, u is 0, t will remain as t. So anywhere you see x is 0. X is here. If x is 0, x is here, is 0. So this one will be sin 0. Sin 0 is 0. This is cos p. If this one is 0, cos 0 is 1. So we are going to have u is 0 already. So it will now be c1 exponential minus p squared t times c2. That's what we are going to have. So between these two guys, which of them will be 0? It is this c2. Because exponential function will never be 0. So c2 is 0. If c2 is 0, how will our new solution be? Our new solution, u will now be what? c1 raised power minus p squared t times c2 is already 0. It remains c3 sin px. Alright? Yes. So after that, put the other condition. What is the other condition? U of L comma t equals 0. It means that when x is L, the u is 0, right? So this u is 0 when x is L. C1 exponential minus p squared t c3 sin pn. Alright, x is L. Now, what are we going to equate to 0? I will not say C3 again, because if I say 3, I'm going to have 0 solution there. It's not possible. And I'm not going to say C1. If I say C1 is 0, everybody here is 0. So everything is 0. So we are going to say, and we can't say exponential function is 0. Exponential starts from 1. So this one is not 0. This one is not 0. This one is not 0. Definitely it's this sin PL that will be 0. So we say that sin PL is 0. So what value of sin is 0? Sin 0 is 0. Sin 180 is 0. Sin 360 is 0. Sin like that, 0. So sin pi. So if sin PL is equals to sin n pi, alright? Sin cancel sin, it means that PL equals to n pi. What are we looking for this time around? We look for P because we define P here now. So P is equals to n pi over n. N pi over n. So if P is n pi over L, where is our new solution? Our new solution is this. So our new solution will be U equals to C1 exponential minus P squared T C3 sine, anyway C P put N, oh, go to here, P is P squared, that's minus N squared pi squared over L squared T, alright? Then times C3 sine P again, N pi over Lx, alright? So that is it. We are done with this. It made this one condition, but we still have two constants. So we collapse this one. Let's say C1, C3 now. Let's call it Cn. If I say this C1 and C3 is Cn, so that there will be one constant. So U equals to Cn exponential minus N square pi square over N squared T times sine N pi over Lx. Alright? Now, what is this now? Now this Cn that I define now, what have I done? I've discretized, like I've turned this continuous to discrete, Cn, C1, C2, C3, C4. And when you discretize something, instead of integral sign, you change it to summation sign. So this Cn that I define here now, I'll say U is equals to summation now, because n is counting. So I'll say summation Cn e raised to power minus n square pi square over n square t sine n pi over Lx. Well, you might be wondering, why did I use summation there and I did not use summation in my previous example? Because that previous example, the last condition is just f of x. F of x is just a function, we don't know it. But here now, that u of x from 0 is already something, sine pi, so we can count. So from here now, when you already know this one as a known function, you introduce summation here, Cn. So n starts from, we're having 0 here, 0 to infinity or wherever. Now put the last condition. The last condition will find this Cn guy. So what is the last condition? U of x comma 0. It means that when time is 0, that u is something 3 sine n pi x, right? So put 3 sine n pi x here. 3 sine n pi x is equals to, now if t is 0, right? T is here. That means everybody here is 0. And e raised by 0 is 1. It will now be summation n from 0 of Cn sine n pi over Lx. Let's say our n starts from 1. What is the meaning of summation? Counting, right? If you do it for C1, if n is 1, it means this will be C1 sine, if n is 1, sine pi over Lx plus, right? If n is 2, C2 sine, if n is 2, 2 pi over Lx, let me count one more, C3 sine 3 pi over, why am I doing this? Why I did not do it in the previous example? I know this as a known function, so that is why I'm counting. Is equals to 3 sine, is equals to 3 sine n pi x, right? So now if 3 sine now, C3, hold on, let me take some. Okay, do I even need to count? I don't even need to count. If this, I don't even need to count. So if this sine pi x is this, that means my Cn is this constant. So it does not even need. I did mean I have, like, they gave me 3 sine 1 now. I already know that the one that is sine pi x now, it will be my C1. So let's not even bother to count. So it means that Cn is already 3 and sine n pi x is equals to sine n pi over Lx, right? So what are we going to do? Sine cancel sine, n pi cancel n pi. Oh, that I supposed to cut sine n pi x is equals to sine n pi over Lx. It means that n pi x is equals to n pi over Lx, right? N pi cancel n pi x cancel. That means 1 over L is 1. L is 1. right? Because nothing will be here again. So L is 1 and Cn is 0, so we are done. But you return it back to your final solution. My final solution will be U equals to, well, I already know Cn to be 3. That will be summation 3 e raised to power everybody here. E raised to power minus n square pi square over L square t. Oh, L is 1. So I don't need this. I don't need this. Alright? Sine what? I already know that L is 1, right? Sine pi is fine. That's our final solution. It's in summation form. So that is how we solve each equation. It's easier than the other one. So with that algorithm now, you can solve Laplace equation. Laplace equation will just be d square u dx square d square u dy square is something. Then you start solving with those conditions. So thank you.